In this video, we're going to talk about a couple of theorems that involve inverses of group elements. Now, one thing I want to invite you to do with this video, this is a little bit different from most videos because I'll be just proving a couple of theorems. So I'm going to start by writing down what those theorems are, and then I'm going to give a pointer or two about how you might approach proving those theorems, and then I'm going to invite you to just stop the video. Just stop watching. I'm recording this video in the hopes that you will not watch the entire video. And the reason is I'm going to give you the theorems and give you some advice about how to prove them. And then I will go ahead and offer proofs of the two theorems. But what I want you to do is just listen to the theorems that I'm going to state. If you need to or if you want to, listen to the advice and then try to prove them yourself. And then after you've tried to prove them yourself, if you think you have a proof, if you'd like, go ahead and listen to the rest of the video and see how your proof compares to the one that I came up with. It might be different. It may be different and still be correct. Just keep that in mind. And you don't have to watch the rest of the video. If you are confident in your proof, then that's great. You should just be confident in your proof and not need to watch the rest of the video. Okay, so that was a 1 minute long preface, so let's get with it. So here are the two theorems I'm going to prove. Number one, I'm going to prove that if A and B are in G, A and B are group elements, G a group, then AB inverse is equal to B inverse A inverse. And Gallian calls this the socks-shoes property. And I might say a little bit later about why it might be called that. And then theorem number two that I'm going to prove is if A belongs to G, a group, then A inverse inverse equals A. So those are the two theorems. If you want to stop now and try to prove them, then you are very welcome to do that. Here's the advice I'm going to give. To prove something is the inverse of X, and I'm putting X as a capital letter because X could stand for, well, X will stand for a group element no matter what, but maybe X is some fairly complicated expression like AB. Okay, now that doesn't mean that X isn't a group element. I mean, what I've underlined there, it's not just a product of two group elements. It is a group element because the operation has closure. But to prove something is the inverse of X, do this. Multiply it by X on the left and the right, and get the identity. Because if you do that, because we know that inverses are unique, I think we proved that in the previous video, because we know that, that inverses of group elements are unique, if I can multiply something by X on the left and the right and get 1, that makes it not just an inverse element of X, that makes it the inverse of X. So that's all you have to do in order to write one of these proofs. So now I really do want you to go ahead and pause the video, stop the video, do whatever you got to do so that you can have a little room to think and try and write up a proof. All right, so I'm going to go ahead with the proof. If you haven't paused the video yet, this is your last chance. All right, so here's how we're going to prove number one. So let's suppose, or let A and B be elements of G. All right, then to show, so here's the thing. I'm going to take this expression here and I'm going to prove it is the inverse of AB, because that's what we're claiming it is. We're claiming it's the inverse element of parentheses AB, whatever the product of AB is. All right, so to show B inverse A inverse is the inverse of AB, we multiply. So I'm just following my own advice here. So we have B inverse A inverse times AB, and I'm trying to be as careful as I can be with the idea that the operation only operates on two elements at a time. That's why all the parentheses. The expression I have here currently makes sense. This is a product of two things, this is a product of two things, and hence this is a product of two things, this thing and this thing. But now I'm going to reassociate some things. I'm going to reassociate so that I have B inverse A inverse A, all of that in parentheses, times B. And by the way, if you want to write the proof without being quite as careful about parentheses, that's okay, because we know the group operation is associative, and you can just sort of do all those steps implicitly at this point. That wouldn't offend me at all. I'm going to reassociate now, so I have A inverse and A together, because now that puts focus on these two dudes. I'm I know that A inverse is the inverse element of A, so multiplying that gives me the group identity. Yay. So that means, move down a bit, so that means I have just B inverse there, because B inverse times the identity is just B inverse, and then B inverse times B is 1. Yay. So that's half of the proof. Here's the other half. I need to multiply on the other side by B inverse A inverse and see if I still get the identity. All right, now, by the way, one thing that is actually true, if we know that something is a group, and we know that multiplying on the left by this gives me the identity, it actually can be proven that multiplying on the right also has to give you the identity. I'm not assuming that theorem right now, so I'm going to go ahead and prove both of these computations separately, but that actually would be something you could prove. So here I'm going to reassociate so that I have AB times B inverse all in one operation there, and then associate again so that I have B and B inverse together. All right. So now that gives me the identity there because B inverse is the inverse element of B, and that's what that means. A times the identity is just A, and then A times A inverse is 1. So all of this means, I can say, therefore, B inverse A inverse is the inverse of AB. Okay, and I'm putting this in brackets, so the next thing I write is not ambiguous. It's the inverse of AB, which means it is AB inverse. So what throws us off a little bit, or what can upset our equilibrium a bit about this theorem here, is that the statement of the theorem looks very, I don't know, it looks very computational in its nature. It looks like I'm trying to take these two expressions and somehow simplify one so that it's equal to the other. And actually, that wasn't my strategy at all. Maybe there's some way I could have done that. I'm not sure. But really, the way I wanted to think about this was just take this and prove it is the inverse of this. I love that highlighter tool. So that's the strategy. Just step back, not start doing algebra right away. Just think about the meaning of the statement that you're trying to prove. Okay. Now, if you did all of this, if you watched all this without pausing the video, okay, first of all, shame on you. You were supposed to pause the video and work on this. But now I really want you to pause the video before working on, or before I start proving statement number 2. You should work on number 2 before I show the proof of it. All right, I'm going to go ahead because this is a video and it makes no sense to just sit here for 5 minutes and wait for you. But you should be pausing the video. Okay, so let's do this in a different color. That'll work. That's like maroon. That's my undergraduate school color there, Texas A&M. All right, so let's do the proof of number 2 over here. I'm going to follow the same strategy, and I will go ahead and do the multiplication on both sides. So I'm trying to prove that this, A, is the inverse of A inverse, because that's what this statement is saying here. It's saying that A is the inverse of A inverse. So I'm going to prove that by multiplying. Now this is going to seem really ridiculous because what I'm going to end up doing is just multiply A by A inverse. We know A times A inverse is 1 because that's what it means for this thing to be the inverse of this. And we know this is also 1. So what this means is that multiplying A on either side, oh, that yellow is hardly visible. Let's change to a different color there. There we go. We know that multiplying this on either side by this element, A inverse, gives the identity. So A, by definition, is the inverse of A inverse. So A is equal to A inverse inverse. And equality is always symmetric, so I can always just rewrite this the other way. In fact, I don't know why I didn't do that in the first place. Okay, so anyway, those are the 2 proofs. I hope that you had some success proving these on your own. But if not, there are some other theorems in Gallien's book that involve inverses, and I invite you to try those using the same strategy. For example, there's one that asks you to prove, this is just a preview here, and I think this is a nice exercise to try. There's one that will ask you to prove that if you have a bunch of group elements, A1, A2, up to, let's say, AK, and you want the inverse of those, well, that's equal to the inverse of AK, the inverse of AK minus 1, and so on down to the inverse of A2 and the inverse of A1. All right, so if you had success with these, or if you didn't have success with these, then try proving this. And remember that any reasoning that happens behind a ... we usually consider a little bit dubious, so a good thing to try is using mathematical induction to prove this.